I see 11 people logged in so far. So we'll get going in a couple of minutes. Before we start talking about things for lecture, let me show you the equation page that goes with the metathesis lab. This is on Canvas so that you can make sure you're actually doing all of the appropriate equations that are for that particular lab. Let me see if I can do the screen share for this. All right, so this is the equation sheet because there are 11 reactions, which on your metathesis lab are labeled A through K. So if you look through, as I kind of page down, it starts with the acid-base reaction of hydrochloric acid and sodium hydroxide. B and C are gas-generating reactions. And then from D all the way down through K are all of the ones that are the precipitation style reactions. You can do the complete ionics, although it doesn't provide a place for you to do it on this page, but I'm not specifically looking for those. I am looking for the moleculars and the nets. So keep in mind that there should be 22 total equations when you are done filling this out. You can do it digitally if you want to, or you can handwrite it. That's up to you. If you download the page, you can also spread the lines further apart if you want more space to write in, since it's just a Word document. I know that there was some confusion. A couple people said that they weren't sure where that was. It's in Canvas in the module. It's like up close to the top of the page. When you read the instructions for how to do the metathesis reaction, it says, here is the page on which you're supposed to put your equations. Questions about that? Because I know I have my two separate groups, my A group, my B group for lab, and there's also other people who have somebody else for lab, but we're all doing the same labs this semester.
This in the end of this metathesis dry lab, you say it's probable that you will need to do the either type or you might wish to use the EQ sheet file. Where is that?
The equation sheet file.
I thought it's like something like a table of solubility.
No, it's just the file that's up at the top of the page.
I got you. All right.
Got a couple more people logging in. But I figured I would try to provide a reminder for that. So I know there was also a little bit of confusion because since not everybody has me for lab, I think Mr. Wheaton's section of class for the limiting reactant, because there was a flood, there was a leak underneath one of the sinks in the lab about the middle of last week. And I had all my B group people last week had lab per usual. My A group people had lab last night per usual, but I think that there was not lab for some of the people who have Mr. Wheaton. You might want to double check.
For everyone who does, he's canceled the next lab for both groups.
Okay, for both his A group and his B group.
Yeah, both of them canceled that
Okay.
lab.
I wasn't sure. I mean, he sent out a message to me that, or a message to everybody in the department that basically said some of the lab sections were not going to happen. But since because Monday is actually the end of the lab week because of what happened for Labor Day. Um, all of my people have limiting reactant lab, but I guess that means his people don't. And then a few of you, I think, have Dr. McHugh. I'm not sure what he did either. I don't know if
We
he.
met over Zoom, although I'll
Oh,
admit
okay.
I didn't.
So he did something for lab, just not in the lab.
Yes, ma'am.
Okay.
Just one little question. Also in this meta thesis equation sheet,
Mhm.
do we have to put which compound is aquatic, which is solid, which is liquid?
Well, for the molecular part, it doesn't actually make a difference, but you have to know which one is the solid in order to do your net ionic.
How we do that again? Do we have like some like a table to see if it's soluble, if it's aquatic?
One of the handouts. I don't know if I can. Hang on a minute. Let me see if I can pull up my other, because they're in the. There's a thing that's referred to as on one of the pages in Canvas. It says something on along the lines of useful handouts, and I'm pretty sure that I loaded the solubility rules, which are actually in your textbook. They're in your textbook also, but this is like the short version.
Oh, okay, yeah, I saw that one.
And it should be one of the handouts.
So if it's
It's not really a handout, it's a digital handout. It's in Canvas on one of the pages that's close to the bottom of the list of pages.
So if it's not fall to that rules, which means it's probably solid or liquid, right?
I don't there should not be anything in that lab that does not follow the rules.
So they're all soluble?
So no, okay, if everything follows the rules, for instance, one of the reactions involves silver chloride. So that's your solid, because the number 3 rule there says most chlorides are soluble except silver, lead, and mercury. So because one of those reactions generates silver chloride, that tells you that that specifically is the one that is the precipitate, is the solid.
Okay.
But there's definitely nothing that doesn't follow the rules there. I didn't pick, we did, when we designed that lab, we didn't pick any like really oddball ones that are exceptions to the rules, because the rules have their own exceptions in it. And like I said, there is another version of that set of information in your textbook, but I cobbled together all of the pieces from a different textbook to make it kind of all one set of rules. There is also a set of solubility rules in the back of your lab book, which I have my lab book in the other room somewhere, but one of the appendices also gives you a different, it's the same rules, it just presents them in a different way, and it should give you all the same data in terms of what is soluble and what is not soluble. There are no rule violators for the lab. Let me shut my extra files so we can talk about thermochem. So we did just a little bit of the thermochem last week. Yeah, I'm losing track of my days. I'm going, yeah, it's Tuesday, isn't it? We talked a little bit about the kinetic, the thermal, and the potential energies. We kind of sort of watch the Roadrunner video. So we're going to pick up here with talking about the law of conservation of energy, which is really awfully similar to stuff from the first couple of chapters. One of the things we did in chapter 1, which then got rehashed a little bit in chapter 2, was the law of conservation of mass. Going back to that, it's you can't make it or break it. All you get to do is rearrange it. Law of conservation of energy kind of does the same thing. You can convert it from one form to another, but you can't create it or destroy it. So we get sort of Zen physics going on here, with the idea that in the creation of the universe, all of the energy in this universe already exists. We can make stars out of it. We can have those stars burn. Those stars can create planets, yada, yada. We're a planet, obviously. All the things that are on our planet. All of that energy still exists, even if you utilize it. It's more a matter of usability. So back to the gasoline idea. Gasoline is potential energy. Put the gas in your car, turn your car on, your car runs, it moves. It also heats up the engine block, passively then also heats up the frame and other things like that as the heat is dissipated. That energy does still exist. It's not usable. You can't gather up all of the warm gases and warm air around the engine and the car and trap it and reutilize it. Once we've sort of, utilization of energy is kind of a one-directional event. Once you've changed its form, you can't kind of gather up the leftovers and change it back again for the most part. There are some ways that you can minimize it or make it more efficient, but you can't kind of go back in the opposite direction. So that's one thing that's a little bit different. You're not destroying it. You're just rendering it unusable. So again, kind of physics overlapping with chemistry here. So all the frictional heating that happens is tied into your transfer of energy. We need to be a little bit more abstract about this. This is something we talked about very briefly back when we were doing conversions between Celsius and Kelvin and Fahrenheit. Temperature reflects the random motion of particles in your substance. Warm things move fast, cold things move slow. That's kind of intuitively logical. But it also means that we can define temperature in kind of any unit that we want to. We talked a little bit about the difference between boiling water versus freezing water when we were talking about Celsius, Kelvin, and Fahrenheit. The idea being that both of those are physical events. We've got freezing of water or melting of ice to turn back into water, or then the cross between going from liquid water up to gaseous water. Both of those are physical changes. But depending upon which unit we're using, that's giving us measurable values. Temperature itself is more abstract. Heat's another thing that gets talked about in this chapter. Again, this is a crossover between physics and chemistry. Heat is transfer of energy. If you take a Coke can out of the fridge and set it on the countertop, and you come back 3 hours later, it's no longer cold. The heat from the air and the countertop has gone into the can to render it down to room temperature. You could also do it kind of in reverse. Pour yourself a hot cup of coffee, forget about it. Come back 3 hours later. It's not hot anymore, probably, unless you had a nice, really, really good thermos. It's cooled down to room temperature. Both of those cases are a transfer of energy. The energy transfer is due to the temperature difference. Okay, third example. Take the can of Coke out of a cupboard and sit it on the countertop. No transfer of energy. The cupboard wasn't hotter or colder, presumably, than your countertop. There's no heat transfer because there's no temperature difference. All of this also ties into work. Work, from the physics point of view, is force acting over a distance. If you have been through physics already before taking this class, one of the things that physics talks about is the pathway. So force acting over a distance involves figuring out where your pathway is. Technically speaking, if I walked from one end of a room to the opposite end and back again, technically speaking, no work has occurred because my pathway is 0. In more realistic terms, you'd have to say, well, it was a positive value going in one direction and it's a negative value going another direction, because you're probably measuring X and Y values in terms of your pathway. We pay a little bit less attention to that idea in chemistry, but it's not invalid. We just tend to not worry about directions in chemistry the way the physics does. You're also going to see some talk of this thing called a state function. And note that the definition there says that the property depends on its present state. So think about this a little bit like a snapshot, okay, which we all take with our cameras or our phones these days, because the cameras are built in for the most part. Take a picture, not a video, a picture, okay? For that moment in time, it shows the state of whatever it is you are taking the picture of. If you're dropping a ball, you might get a blur from the motion depending upon how fast the shutter speed stuff is on your camera, but it's really only going to show you a piece of the blur. So we're not worried about what came before. We're not worried about what's coming afterward. It's like this moment in time, this moment when we are taking a measurement, which impacts the way we assess it. We're going to divide that assessment into kind of 2 big chunks. We're going to call them system and surroundings. So think about the lab, since some of you had lab last night. If you have a beaker full of stuff, and in fact, last night, what we were creating was a precipitate because we then later filtered that precipitate. The system is the beaker, the water, the 2 chemicals we put into it. You could also, if we're talking about the cooking phase, you could also say possibly the system includes the hot plate that we warmed up the beakers on. All of that's the system. Now the surroundings are you, whoever's across the bench from you, the air, the bench top, the rest of the building. It's not like those things cease to exist. They're actually still there, but we're not really paying attention to them. So we're going to designate them the surroundings. Why do we need to divvy this stuff up into halves anyway? It has to do with directionality. Directionality, not like the physics thing of there's an X and a positive X or a negative X, but kind of an in or an out idea. Exothermic is the term that, one of the terms that we are applying here. Exothermic means evolution of heat. Things get hot. So if you strike the match on the box and it lights the match and then you light the candle, okay, all of those things are creating heat. Therefore, they are exothermic. If you plug sodium, water, and like fraternity into YouTube, there is a video, or at least there was a video that shows not as a demonstration where when you drop sodium in water, usually you're using a gram or two of sodium, pure sodium, not sodium chloride, pure sodium. And you drop it into a beaker and you get this little fizzing and you get this little tiny itty bitty flame that's about 1/4 of an inch high for about 3 seconds as it burns off all the hydrogen. And that's kind of the end of it. The video, such as I remember it, involves a couple of guys and a galvanized steel bucket out on the front lawn of a building. And they have this ridiculously large chunk of sodium. It's like 1 kilogram of sodium. And they heave it into the bucket and it sort of detonates. Either way, big scale or small scale, it's exothermic. Exo, think about that in terms of exiting. Your heat is flowing out of the system. It is going toward the surroundings. So exo and exit kind of go together. Reverse. Endothermic is absorption of heat. Now, granted, as human beings, we don't tend to logic our way through it exactly like this. We tend to think of it as, oh, something got cold. No, that's actually technically not correct. What's really happening from a thermochemistry point of view is the heat is going into the system. These days, if you buy a prepackaged first aid kit, a lot of times it will come with a little pouch that has instructions that say, like, snap and shake, or lay it on a hard surface and hit it with your fist, and then you shake it up. Basically, what you're doing is you're breaking an internal packaging so that the two things actually mix. And you get something very, very icy cold. What's happening is all of the external heat is going into the system. So again, kind of brain tricks here. Endo involves the heat going in. So if we look at this from a little bit more of a molecular point of view, things that hold a molecule together are the bonds. The energy is stored in those chemical bonds. So if you break them, what's happening is you're releasing some of that energy, which then, of course, is detected as heat. If you're going back in the other direction, it's not that you're not breaking some bonds, but you are making more than you are breaking in terms of energy. And this increases your potential energy in your system. So the products actually have more potential energy than the reactants. It's kind of a odd, slightly backwards way of thinking about it. So all of this is thermodynamics. Thermodynamics involves all these sort of abstract concepts. We're doing some thermo this semester. If you are taking the second semester, thermodynamics will come around again. It's kind of a 2-part set of information, and you get some of it this semester, and then we revisit it and extend the concepts again in the second semester. So back to Zen physics again. And there's a whole bunch of laws with numbers here. The first law of thermodynamics says the energy of the universe is constant. So that goes back to that idea of whatever was there when the universe started is actually still in existence, at least in this universe anyway, multiverses notwithstanding. And it did something. It either got utilized so that it's less usable, it got transferred from one place to another place, but it's all still there. We are going to embrace a little more math here of, we're going to give it a sign, as in plus or minus sign. We're also going to assign a letter of the alphabet to it. It doesn't actually matter whether your letter Q is uppercase or lowercase. It's sort of textbook dependent. I've seen some textbooks use a capital letter Q and some use a lowercase. But as long as it's a Q, it doesn't really make a difference. If your Q is positive, this is considered to be an endothermic process. Okay, back to the idea that you are gaining heat from the surroundings into the system. This is why they're calling it a positive value. The opposite end of it, if your heat is flowing out of the system into the surroundings, we are going to call it a negative value, because it really is all about the system. The system being the important part and the surroundings just being the everything else. So if you are gaining heat as a system, it is positive. If you are losing heat as a system, it is negative. And more abstract things here. If your two objects are at the same temperature, this is called thermal equilibrium. I believe in physics, they refer to it as an adiabatic system because you're not gaining or losing. You might run across that term. It's also all about your directional flow, because heat goes from the hotter to the colder. Yes, I know that makes you think that air conditioning shouldn't work, but air conditioning is fueled by electricity, which is energy. So you are utilizing energy to make it go backwards. We also need to be able to have some units. So one of the units that we mentioned a little bit in the gas laws chapter a week or so ago was joules. Also calories, not that we talked about calories in gas laws, but calories is also a way to measure energy. We tend to think of calories as a food measure, which is not wrong. I'll come back to that in a moment. But for joules, it's actually a compound unit. And one of the reasons that the root mean square velocity equation works the way it does is once you take the square root of something that has a kilogram, a meters squared, and a seconds squared in it, you're reducing it all down, because kilograms cancels out. Remember that in root mean square velocity, your kilograms is on the bottom of what goes underneath your square root symbol. So kilograms cancel out. And then meters squared over seconds squared, if you square root that, you're left with a speed, meters per second. So 1 joule represents accelerating 1 kilogram that was already traveling at 1 millimeter per second, so that it then accelerates 1 meter per second. This is why it's squared and squared. The calories have a different origin in terms of what they represent. It is still a concrete thing, but it's a concrete thing in terms of it actually relies on a particular substance. Calories are based upon water. If you want to get down to all the nitty-gritty details here, it's the amount of heat required to raise the temperature of 1 gram of water, so roughly 20 drops, 1 cubic centimeter of water from 14.5 Celsius to 15.5 Celsius. Its origin sort of started before metric system came into existence. But then we need a way to convert back and forth because calories are sort of tied into the English system. Not exactly, they've still got grams and Celsius involved, but it's not a straight one-to-one conversion. Calories are bigger than joules. Your conversion is 4.184. So 1 calorie needs or is 4.184 joules. So now we need to revisit dimensional analysis a little bit, just because it doesn't go away. Now back to the food calorie thing. I can't remember which comedian said calories is a measure of food yumminess, as opposed to a more physics description. But a food calorie is actually in chemistry a kilocalorie. So you could say 1 kilocalorie would be raising 1 kilogram of water by a degree Celsius. So a food calorie is 1,000 times bigger than a regular calorie, calorie in chemistry and physics. So let me talk about a couple of conversions here. Some of them are straight one-to-one conversions. If you have 120 joules, it's not a very large amount of energy, and you want to convert it over to calories. Set up your conversion, make sure your calories are on the top and your joules are on the bottom. That way, when you multiply, joules will cancel out. Mathematically, we are basically doing 120 divided by 4.184, and that gives you 28 and a little bit calories. What if you needed to do it in 2 steps? What if you had 34 kilojoules? So kJ, kilojoules. I did this one in 2 steps. I converted it from kilojoules to joules alone by multiplying by 1,000. And then I did my division by 4.184. This one gives you quite a few calories, 8,126.2. Sometimes you will also see just conversions between calories and kilocalories, as well as, and I didn't give you an additional example, but you might also see conversions between joules and kilojoules. Same premise. Kilo means 1,000. If I have 43,000 calories, if I divide by 1,000, that's going to give me 43 kilocalories. So some of these conversions will pop up in some of the equations and some of the other things that we encounter in this chapter, as well as the lab. One of the labs that's coming up, it's actually almost a month from now because of our weird rotation. We are going to do part of the calorimetry lab that is in your lab book. We're going to do a little bit of something called specific heat And we're also going to do some heat of reaction. So those are things that you are probably going to have to do some conversions for. All right, so switching gears just a little bit. How do you figure out how much energy it takes to heat something up? Water is a typical, almost stereotypical way of dealing with this. Calorimetry, which is why the lab is called calorimetry, the science of measuring heat. We need a couple of different more buzzwords here, one of which is called heat capacity. Now, heat capacity alone doesn't tell you what you are measuring. It tells you how much and what the temperature change is, but it doesn't tell you what the thing is you're measuring. You can have a heat capacity for a number of things, okay? It says amount of heat needed to raise the temperature of a given sample by 1 degree Celsius. So think about this as like, if you're gonna microwave something, if you have a really small cup that's only half full of coffee versus trying to nuke, let's say you're making like pudding or something like that, and there's half a liter, 2.5 cups of liquid, and you stick that in the microwave, you're gonna have to cook it longer because it's a bigger amount. Therefore, that ties into the idea of heat capacity for a large sample is going to be different than for a small sample, even if it's the same item. On the other hand, since it doesn't tell you what it is, heating up a nail in a fire is going to be different than heating up a tea kettle over a fire. Different substance, different mass. So I went back to the idea of water. Heating up a bathtub full of water takes a lot more heat than heating up a teacup. Now let's narrow the field a little bit. What if it is a particular amount that you are heating? So note, there's a really small difference. So heat capacity, this just says amount of heat, okay? I kind of highlight my thing there, okay? Amount of heat. Note down here, it says 1 gram of a substance. So subtle difference there. One of the things that we are going to be doing in lab is determining the specific heat of a metal. Now look at the units. It's another compound unit. We've got joules per gram Celsius, or you could do it as joules per gram Kelvin, keeping in mind that a Celsius degree and a Kelvin degree are the same size degree, even though they don't start at the same place. You also see that there's this weird kind of overlap in that if it's 1 gram of water by 1 degree Celsius, wait a minute, didn't we already see that? That's what a calorie is. So we have 3 overlapping terms here that all have a lot of similarity. And if I scroll back up here, we've got 1 gram of water, and actually, let me undo that. There, 1 gram of water, and it's 1 degree Celsius. Oops, I moved things that I wasn't supposed to. But that gives you there. 1 gram of water by 1 degree Celsius. So 3 different terms, 3 very subtle differences. Make sure you kind of keep track of the idea that there is a difference between these 3 things. Calorie has to be water, has to be 1 gram, has to be 1 degree. Back down here, heat capacity, just 1 degree. Doesn't say how big it is and doesn't say what it is. And the specific heat, that one says 1 gram and 1 degree. It just doesn't have to be water. Now, one of the things we could do, although this is not actually specifically the purpose of the lab, is you could use specific heat capacity to identify something. Different metals have different specific heats, the same way that different metals have different densities. Water's specific heat is the calorie. It is 4.18 joules per gram, 4.184 joules per gram Celsius. So think about it this way. Okay, you have 3 liters or so of blood in your body. And because water has one of the highest specific heats of normal, average, everyday stuff, if you didn't have that same high specific heat, think about walking down on the beach in like August, okay? It's 102 or something down on the beach. If you didn't have water with a high specific heat capacity, your blood would boil because it would absorb the heat way too fast. So there is a reason why most living substances on Earth are water-based. Now we encounter an equation. Q equals Cm delta T, and yes, my Q changed cases in this voice. It's a capital Q. It doesn't really make a difference though. Q equals Cm delta T. So we need to think about what all these pieces actually represent. Q is heat. Usually it's in joules. However, you could do it in calories. C is the specific heat for whatever it is you're looking at. Sometimes it's water, but sometimes it's something else. Because of the units, joules per gram Celsius, your mass must be in grams. And the delta T, keeping in mind that in chemistry and actually sort of in physics too, that the triangle, which is a uppercase delta, is change in temperature. And I know it's kind of weirdly subscripted there. TF minus TI, temperature final minus temperature initial. So it actually makes a difference whether you're heating something up or cooling something down as to whether you're getting a positive Q or a negative Q. So I have some examples, how to solve for different things here. If I have 145 grams of water, cupful, and I want to go from 22.3 to 75, I need to start putting all the pieces into my equation here. Part 1, what's my temperature change? Okay, well, it went up to 75, but I started at 22.3. What's the difference? 52.7. The 4.184 is water's specific heat, so that's got to be put in. And then my M is the 145. I have quite a few joules, but remember that joules are awfully small. I have 31,972 joules. But you have to also be able to solve for the other things in the equation too. So I did my next one looking for my temperature change. This one doesn't involve water either. Iron, and there is a little table in your textbook as well as a little table in your lab book that tells you 6 or 8 of these standard average metals and what their specific heats are. I'm going to use 50 joules of heat and 10 grams of iron. How much does it warm up? So put all my pieces in. Q is 50. My C, this is the one I looked up, is 0.45. I have a 10-gram piece. Delta T is my unknown. So I did my little algebraic rearrange here. I took the stuff that was multiplied together that I knew and brought it to the bottom over here on the other side. Finish my division, and I get 11.1 Celsius. Kind of like I did my rounding back in chapter 1. I wasn't actually using sig figs for this. I was rounding it to the fact that if I was using a thermometer in the lab, we have both digital ones and non-digital ones. I'm never going to be able to read more than 1/10 of a degree in what we have available. So I left it at a single 1/10 there. What if you had to solve for C? What if you didn't know what your thing was? And this is actually one of the things we're going to be doing in lab. The idea is you're going to have a mass of metal and you're going to do things with it in order to figure out what the specific heat is. If I had 75 joules, and I know my metal weighs 14 grams, and I also know what the temperature change is. It started kind of cool at 10 Celsius, and it went up to room temperature-ish at 22 Celsius. This is another one where I'm going to put all my pieces in. 75 for Q, C is my unknown, 14, and then 22 minus 10. Do all my rearrange here. I end up with 75 divided by 168. My C value is 0.446 joules per gram Celsius. One of the things that you will notice if you actually look through, oh, and I thought I had put pictures in here, phooey. I'm gonna have to see if I can pull up the picture. One of the things that's true about metals, all the metals that you are likely to encounter have values less than 1, point something. So they're all decimal numbers less than 1. We are going to use a calorimeter to measure heat absorbed and released, which then goes back to the whole calorimetry. Now I have to see if maybe I can actually pull up a picture to share. Let me see if I can get this to work. All right, let me share this. Yes. All right. So let's talk about bomb calorimetry for a moment. We are a community college. We don't have a bomb calorimeter. However, this is how they work. If you have ever wondered how they figure out how many calories are in your Snickers bar, this is how they do it. So note, going from the outside inward, we have a big steel bucket and a slightly smaller steel bucket with an airspace in between for insulation. Inside the inner bucket, there is water. And there is a smaller bucket yet, where it's kind of that pale purple color, that has this thing that looks like a light bulb filament at the bottom of it. That's your ignition coil. So not only is this a multi-layered event here, it also has, and I don't know if you can see where my cursor is, it has this thing up here that says oxygen supply up here at the top. And the oxygen supply goes all the way down into the innermost bucket. Basically, you take a slice of your food item and weigh it. You put it here in the crucible, also sometimes referred to as the sample cup. You pump pure oxygen into the inner chamber and screw the lid on really tight. It's an airtight seal. You have a thermometer, and note, the one in this picture obviously looks like a real thermometer, or looks like a regular alcohol / mercury thermometer. In reality, these days they use a thermocouple to measure the temperature. And what you do is, since it has ignition wires, after you have this entire thing set up, you push the button and it goes boom. It goes boom in a very controlled, measurable way that incinerates everything that is burnable in your food sample, because your body technically is capable of extracting all of the energy in the bonds of that food sample. Well, they're doing it all in one giant bang. Obviously, in digestion in humans, this is a multi-step process that doesn't go boom. Your digestion takes a while. But bomb calorimetry is a really accurate way to measure how many joules or how many calories are in a food substance. We, being a community college, go low tech. And if no, it doesn't actually show me. It was supposed to have the coffee cup calorimeter picture. Phooey. Hang on for a minute. Let me find the other picture, because otherwise it won't. Make much sense. All right. This, on the other hand, is wrong. Okay. I think somebody's microphone went weird. Let me try this again. All right. Being a community college, this is the technology that you're going to use. Okay. This is known as the coffee cup calorimeter, which looks absolutely Mickey Mouse and actually weirdly works pretty well. So if you have 2 styrofoam cups, therefore you have 2 buckets with an airspace, you'll have water on the inside, you'll have a cover, which actually we tend to use just pieces of cardboard because it's easy, and you'll have a thermometer stuck down through the top. And once you add your reacting substances into the middle here, you can measure how much temperature change there is. And there's an equation that is tied into the Q equals CM delta T that we're going to be using in order to do the calculations. So yeah, we unfortunately for this thing don't have high tech involved. We have pretty low tech involved. And you'd think that it actually probably shouldn't work at all, and yet it really does. So coffee cup calorimetry, the nested styrofoam cups is what we're going to be doing in lab. One last little bit here. So it's all about the heat transfer. So you're going to heat up a sample of metal. You're going to heat it up in a big test tube so that it actually stays dry. And then you're going to pour the hot metal using one of the test tube clamps, so you don't have to use your fingers, into the water. Okay, and think about it this way. If you drop a hot something into water, even if the water was kind of just average room temperature, the hot something, in this case, the hot metal, increases the temperature of the water you're dropping it into. That way you get a temperature change. So the heat transfer of the water, actually the heat transfer of the metal is negative, therefore the heat transfer of the water is positive, and you get this relatively equal transfer. We can use that to transfer heat, to talk about heat capacity. Depends upon how much you use. So one of the things you have to do in the lab is measure the mass of the metal pieces that you are using once you do this, because 10 grams of metal would give you a different change than a kilogram of metal. So we're going to end up looking at it in terms of how it relates to the mass of your sample versus the water, which is a fixed value. Water is that magic 4.184 value. And we're going to use those two ideas to kind of allow you to calculate specific heats for the metals. That's part of the lab that's going to get done. This gets us about halfway through the chapter. Are there questions about homework that is due before midnight tonight? I noticed that I saw 9 submissions listed on Canvas, so some people have already turned it in. Are there questions about that?
Yeah, there's one question about standard temperature and pressure.
Hang on, let me grab my pages. Yeah, figures I have all this stuff jammed in a binder, and I'm trying to find out where I stuck it. Oh, okay, there it is. Do you know what question number that is?
Yeah, number 9.
Okay. So that one is a stoichiometry problem.
STP, right?
Yes.
So the question is, in our lecture, it says STP is equivalent to 0 Celsius, 273
Yes.
Kelvin. But everywhere in the internet it says it's 298, not 273.
No. STP is 0 degrees Celsius.
Huh, that's interesting. And then to solve it, which formula do we use? We use P, pressure multiplied by volume equal. No,
Because it's a stoichiometry problem. It has the three standard steps in it of I gave you grams. You have to convert grams over to moles. I gave you a balanced equation of which I am only interested in water and ammonium nitrate. And then it asks you how many liters. The magic number that goes with the entirety of the chapter is 22.4 liters per mole.
It's a volume, right?
Yes, 22.4 liters per mole for all gases at STP.
Okay, yeah, I quite didn't understand how it works, because the way example that you gave us in the lecture, it's contain only two components, like mercury O.
Mhm.
It's divided to mercury and O2. And then in examples, you make it like on top it will be oxygen, and the bottom it will be
Right, because
mercury O.
that one was a 1-to-2 ratio.
Right. But here we got three components. So what are we doing?
But
here?
you're only interested, it says, I only gave you data for ammonium nitrate and it only asks you about water vapor. You only need two components. The rest of it makes no difference other than balancing the equation.
So what do we use? Like only the water and
And the ammonium nitrate.
oh.
Only
Okay.
use the
And it
pieces
will be
that
ratio.
only use the pieces that it asks you about. All the rest of them do not influence the math.
So the ratio will be 2 to 4.
Yes.
Okay. All right. Thank you.
Yeah. Stoichiometry problems, even with gases, are usually a 3-step problem. Other questions? So I will see if I can get those, for the most part, graded tomorrow or Thursday morning. And then I will post the answer key for the homework set, and we will go over it as part of class on Thursday then. Any other questions regarding this or lab? Lab is sort of a never-ending complicated problem right at the moment.
I was really confused when looking at problem 8. I didn't know where to approach that from.
So for 8, you have a volume, a pressure, and a temperature. You are changing the pressure and you are changing the temperature. There's only one equation that allows you to change all of that at the same time, and that is the combined gas law.
All right. Thanks.
You have to have an equation that has more than one of each item. More than one pressure, more than one temperature, more than one volume.
Yeah, that's what I was forgetting, because all that was coming in my brain was remembering when you said you can only do it like this if the pressure doesn't change or the temperature doesn't change.
Well, so Boyle's law, Charles' law, Guy-Lussac's law only changes one item at a time.
Yeah.
If you want to change more than one item at a time, you have to use the combined one.
All right. Thanks.
Other gas law questions? Other than that, I will see you on Thursday, and we will talk about the answer key to that and continue onward a bit with some more thermochem. Bye.